Okay, we're going to start our second unit. It's called stoichiometry, which is pretty fun, and I know you're going to be stoked to do this unit. You should already have a packet. I handed those out the day before we went online, but if you don't, you can also print it. It's on Canvas, or you can wait until we get back to school and grab one on Monday the 7th, or I can leave one at the office for you. So let me know, any of the above. Okay, so we say the stoichiometry. I just say it kind of fast, stoichiometry. Pretty fun. Okay, and here's just our objectives that you can look at. We need to use our balanced chemical equations again. So we need to make sure that we can write equations and that we can balance them. And we're going to use molar relationships once the equation is balanced to figure out what is going on with our amount of mass. And we're also going to use quantitative analysis, which is just, again, quantitative means numbers, to identify whether or not the law of conservation of mass is being met in a chemical reaction. So those are just some of the fun things we're going to do. You will definitely need a calculator on this unit, so make sure that you are bringing one to class. Okay, there's your first page of your stoichiometry. These are the 4 I can guides. Okay. Write a balanced chemical equation from a word equation. Identify molar ratios, which of course we're going to learn about. Determine molar mass, which we're going to learn about. And then we're going to calculate 4 types of stoichiometry. And this is where we need our calculator the most, is when we are going to calculate and use stoichiometry. Okay, so page 1, if you turn there, this is where we are. We're going to go ahead and fill out this page today. That's our goal. Okay, so we're going to talk about the mole. Here's a nice little picture of a mole. It's a little underground creature. Apparently they don't have very good eyesight. And look at those claws, kind of crazy. There's another front vision viewpoint of the mole. And moles like to make little hills, little mounds. People hate them in their yards. And oh, look, there's a mole on someone's skin. Maybe you're a moley person. Okay, but in chemistry, that's not what we're talking about. We're not talking about this little furry creature with scary, dark, scary long claws or moles on our body. We're talking about a mole in chemistry, which means it's a number relationship is what a mole is. So saying a mole of something is like saying a dozen. So for example, when we say 1 dozen eggs, it means we have 12 eggs. If we say 1 mole of cookies, it means that we have 6.02 times 10 to the 23rd eggs. Okay, that's a huge, huge number. But that's what 1 mole means. 1 mole of anything is equal to this number right here, the 6.022 times 10 to the 23rd. Okay, so let's look at some examples of how large a mole is. These are really hard for me to imagine. And so I mean, this helps to understand how big it is, but it's still really hard for me to imagine. So hopefully it's not as hard for you. So if we had 1 mole of pennies and we shared that equally between all the people in the world, and I think right now we have 8 billion people, it would give everyone $1 million per hour to spend for the rest of our lives. That's how much a mole is. I think that is absolutely insane. I think milk would go up to, like, what do you think? $1,000? Probably more than that, right? Probably $1 million. I don't know. Crazy. Okay. If we have some marshmallows, so these are just our normal average size marshmallows. 1 mole of regular marshmallows would cover the earth in a layer 12 miles thick. Okay, 12 miles. Think about 1 mile. Okay, 1 mile is 5,380 feet, I believe. Imagine 12 of those covered. We would have the fluffiest layer on the outside of the earth. Tastes pretty good too, I bet. Okay, another idea is 1 mole of dollar bills. So if we like have a stack of dollar bills, we put them on top of each other, it could reach a distance from the sun to Pluto and back again if we had 1 mole of dollar bills. That is crazy. Yep, there it is. There's the sun. Okay, very center, and Pluto's way out there. Actually, way out there. And back. Okay, that's how large a mole is. It's crazy. Okay. Oh, and it would not only do this once, but it would do it more than 7 million times. So, you know, that's a large number. Okay, how big is a mole? Right here. 1 mole of water. So if you were to take an amount of water and figure out what 1 mole was, it only has a volume of 18 milliliters. 18 milliliters. So when you get back on Monday, I will show you this visually. But think about like a soda pop can, just a regular soda can. That has 355 milliliters. You're talking about 18 milliliters. It's very, 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 it's just a small amount. And 1 mole of water has 6.022 times 10 to the 23rd molecules in it. Molecules of water. So it's kind of crazy. Here's some funny little jokes for you. Haha. Okay, the reason why we use the mole is because we want to have a way to deal with these enormous numbers. Okay, these numbers are just huge, right? So we need to make a way that it makes more sense and it's more feasible. So remember, 1 mole is 6.022 times 10 to the 23rd. So if we have 1 mole of cookies, oh, cookies, like crumble cookies, my favorite. Okay, 1 mole of cookies is going to equal 6.022 times 10 to the 23rd cookies. If we have 1 mole of sharks, it's going to equal 6.022 times 10 to the 23rd sharks. If we have 1 mole of atoms, it's going to equal 6.022 times 10 to the 23rd atoms. So you're noticing a trend here, right? Just like when we say 1 dozen equals 12, it can be 1 dozen bikes, it can be 1 dozen cookies, it can be 1 dozen rolls, it could be 1 dozen pencils, okay? It always equals 12. Well, 1 mole of anything always equals this number right here, 6.022 times 10 to the 23rd. Okay, just like our little cookie, our little dozen example over there. Okay, now the cool thing is we can use the mole as a conversion. So when we talk about conversions, we're talking about 2 units that equal each other, like 1 foot equals 12 inches, right? So we can use the mole as a conversion when dealing with a number of atoms or molecules or compounds, okay? And this number, because we keep saying it, but we're not putting a name to it, but now we have a name. It's called Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. Okay, so 1 mole is equal to 6.022 times 10 to the 23rd of anything. Okay, paper, money, gallons of milk, paper airplanes, whatever it is. Okay, here's some lovely little memes you can scroll through. Aha! What song is this? I just met you, and this is crazy. That's right. Call me baby. Yep, there's that again. Isn't that Carly Rae Jepsen, I think? Yep. That's disgusting, Mr. Dinosaur. Let's not eat moles on Mole Day. There is actually a Mole Day. It is October 23rd because it's 10 raised to the 23rd. So October 23rd is Mole Day. That's the day I think we should just eat guacamole. Okay. So we just want to make sure that we're okay with moles and Avogadro's number. Okay, now let's talk about molar mass. We're going to switch gears just a little bit. Okay, molar mass is the mass of 1 mole of a pure substance. So now we're using this 1 mole when we're talking about a pure substance. Please remember that a pure substance is anything that's an element. So all of the elements on the periodic table, there's 118 of them, or any kind of compound. Okay, so a compound, remember, is 2 or more different elements chemically bonded. And within that compound umbrella, you can also say molecules. So a molecule is going to be like your Brinkelhoffs, or your covalent bonds. So all of that encompasses a pure substance. And so again, molar mass is the mass of 1 mole of any pure substance. So 1 mole of aluminum, 1 mole of calcium, 1 mole of sodium chloride. Okay, so molar mass, the mass of 1 mole of a substance, okay? And the units that we use is grams. So we have these lovely numbers and they're called grams, okay? That's our unit underneath them. On the periodic table, when we're looking at the mass, it's usually that bottom number. I say usually because some periodic tables, they put them on the top, but on this one and the one that we have, it goes on the bottom, okay? And remember, this is the mass, the average mass of all of the isotopes and how abundant they are. Okay, so hydrogen has 3 different isotopes, and there's a little calculation that we use to figure out what the average of all those isotopes are, along with how abundant they are. Okay, so we can say that 1 mole of hydrogen has a mass of 1.0078 grams. Okay, so by definition, 1 atom of carbon-12 is equal to 12 AMU. AMU stands for atomic mass unit. So we can also say that 1 mole of a carbon-12 atom is equal to 12 grams of carbon. Okay, here's what the difference is. The mass of 1 atom or molecule in AMU, atomic mass unit, is equal to the mass of 1 mole of the same substance. So when we're dealing with moles, we're talking about grams. When it talks about an atom, we're talking about the atomic mass unit. But notice the numbers are interchangeable, okay? The numbers are the same and the units are interchangeable. So we can always just say grams, or we can also say AMU. When scientists were figuring out the mass and how to calculate the mass of all the elements, on the periodic table, they just arbitrarily chose carbon as the mass that they would go off of. So hydrogen is 12 times lighter than carbon, and that's why it has a mass of 1. And then like magnesium, the average is 24, so it has double the mass of carbon-12. So they just chose carbon as the jumping off point to determine what all the other masses were on the periodic table. Okay, so let's look at this. So here's aluminum. That right there is the, what is that? That's right, that's the mass number. Okay, here's neon. Look at it, what's the mass number? Fantastic, it's 20.18. Oh, there's gold. What's that mass number? You're right, 196.97 grams is our unit there. Okay, so there is your molar mass found on the periodic table. Remember, that's your average, but it also means grams in 1 mole. So for oxygen, we can say that 15.99 grams is equal to 1 mole of oxygen. Okay, there's a lovely periodic table. Yours has mass on it, mine does not. But let's go ahead and find the molar mass of rubidium. Okay, there's that one. We're going to go back though. So rubidium is right here. Okay, we're looking at that mass right there. And just to make it easier on ourselves, let's go ahead and only round to the hundredths place. So if we look at rubidium, it's 85.468. So we're going to round the 8 up to 7. So this is 85.47. So rubidium has a mass of 85.47. And we want to put units. Our unit is always grams. Okay. And then go ahead and look at neon. Pause that and look at it. Okay. Did you find neon? Neon's going to be 20.18 grams. And these both equal 1 mole. And it's always going to be of the same substance. So 85.47 grams of rubidium equals 1 mole of rubidium. 20.18 grams of neon equals 1 mole of neon. Okay, notice how those substances are the same. All right, so go ahead and do these 4 right here. Find the molar mass of copper, iron, and calcium, and then come back and double check. Okay, so really fast, copper is 65.33 grams. Hopefully you found that. Iron is 55.85 grams. Calcium is 40.01. Just kidding, 40.08 grams, and gold is at 190.